Hello and welcome to this video. We do have 56. A small ball is tied with a thin rope and moves in a circular motion in a vertical plane. When the ball reaches the highest point, which of the following statements is correct? So the velocity of the small ball is at least square root of gr. The tension in the rope must be zero. The acceleration of the small ball is vertical upward. The small ball is in equilibrium. So for A, the velocity of small ball is at least the square root of gr. So getting back to the mg plus the capital T, which equal to mv square divided by r. This is the net force, or the Newton's second law. The net force is that. This is the m, and that is the acceleration. So at the top position of the small ball, the t, or the ball, in order the ball to keep its motion, the t must be greater or equal to 0. So the minimum speed is when the t is equal to 0. That means the height of the rope is the minimum as well. Okay, so it's 0. In that case, what we have mg would be equal to mv squared divided by r. Simplifying by m, this is the gr would be equal to v squared. That means the v squared, or the v, would be square root of the gr. This is the minimum speed for keeping the ball in the vertical circular motion. The tension in the rope must be 0. That is not a requirement. The t could be either 0 or greater than 0. That, as we say here, it could be greater or equal to 0. So for B, it's not the one, it's A. For C, we have acceleration of the small ball is vertical downward. When it's at the top here, the force is directed to the center as the acceleration ma. So it's pointing downward, not upward. So for D, the small ball is in equilibrium. At this position, exactly this position, the net force is actually the sum of the two. When an object is at equilibrium, actually the net force must be equal to 0. It's not the case here, so the ball is not in any equilibrium. That was for the 56. For the 57 here, we have which of the following statements is correct about the diffraction phenomenon of wave. So we're talking about diffraction phenomenon of waves here. When a wave encounters obstacles during propagation, it will inevitably exhibit a distinct diffraction phenomenon here. For B, diffraction is only clearly visible when the size of an obstacle or aperture is smaller or similar to the wavelength. That is the actually condition to just like observe clearly the diffraction phenomenon. So the wave must have a certain wavelength which is comparable to the obstacle or the apparatus here. So this open area must be something close or smaller than the wavelength, so we can observe the diffraction phenomenon here. So it's not the A, it's the B. The higher the frequency of a wave, the more likely it is diffract. We do have V equal lambda mu, as the speed is the constant. If we are in the same medium, we can observe clearly that the frequency is inversely proportional to the frequency is proportional to the wavelength. So as the frequency getting higher, the wavelength getting very small, and in this case, so the diffraction wouldn't be observed easily. That means to observe the diffraction phenomenon, it would be better to use waves with a very low frequency. In that case, the wavelength would be greater. Diffraction is a phenomenon unique to waves, not particles downstream. The classical physics says that, but the quantum physics doesn't say that, because instead, for instance, for example, here we have, if we have electrons, and electrons are just like fired into a certain obstacles, they will scatter and they will just like show a phenomenon of diffraction. So it's not reserved for only waves, but particles as well can manifest to show a diffraction phenomenon. For the 58, a spring oscillator has an amplitude of A and period of T. If the timing starts from the equilibrium position, the distance it travels in T over 4 is it A or A over 2 or 2 A's, or cannot be determined. For a spring here we have spring oscillator. If we get it, or if we put it, extend it into its maximum amplitude, minus A here, it will oscillate between those two positions. So the timing reference would be at the position of equilibrium. What's gonna be the position of that object at T divided by 4? So let's just like decompose the fall period into 4 parts, from 0 to T over 4, from T over 4 to T over 2, from T over 2 into 3T over 4, from 3T over 4 into T. Actually, when it's getting back from here to here, that's gonna be the T over 4 as a time taken to just like travel this distance. That means the oscillator would be at the maximum extension, which is the amplitude. Okay, from T over 4 to T over 2, in that case is getting back to the equilibrium position. So the T over 2, the oscillator will be at its equilibrium position. For the third part here, T over 2 to 3T over 4, the oscillator will reach the negative amplitude. That means it's getting back to the amplitude in the negative direction. Finally here, the 3T over 4 into the fall period is getting back again to the equilibrium position. So for our case here, the T over 4 would be the timing of the oscillator to reach its maximum amplitude. The 59 here, when two waves meet and superimpose in the same medium, if the vibration direction of the waves is the same, the frequency is the same as well, and the phase difference is constant. So all of those conditions remind us of interference. Those are actually the conditions of what we call coherent waves. If all those conditions met, they would be what we call interference of those waves. We do have two types of interference: constructive and destructive waves. If they are in phase, that means the maximum of the first wave meets with the maximums of the second ones, they would be adding up. This one add to this one gives the clear blue here. The same here, this one plus this one will be giving this large, this one plus this one will give in this large. But for destructive, it's just like a subtraction. If we subtract all these amounts or this distance from all of that, that would give this red line. The same here, all of that minus this will give only that amplitude. So one is distracting the other, but here one is constructing with the other. For diffraction, it's only for one light that met obstacles, or just like a slit, to give bright fringes and black fringes. For refraction, this is the change of direction of the light once it's emerging from a certain medium to another medium which is different from the first one. So that's what we call refraction. Dispersion, this is the experience that we can use just like to decompose a certain light composed of many colors, just like what we do with the prism. Okay, for the light or the white light, it would be decomposed into its 7 lights from red to violet. Finally, here we have the question number 60. Which of the following statements about friction is false? We're looking about the false one. The direction of static friction may be the same as the direction of motion. The magnitude of the sliding friction is always proportional to the normal force. Rolling friction is much smaller than sliding friction. Friction always opposes the motion of the objects. When we talk about friction, what comes to our mind first is that the friction is always opposes the motion. But to correct that, we actually sorry for that. We actually need to say that friction always opposes not the motion but the relative. We have to add this word, relative motion between two surfaces. The relative motion, it's not the motion itself but the relative between the two. Ya is true. A direction of static friction may be the same as the direction of motion. If we take the walking example, when a person is trying to walk, it pushes backward, but the friction imposed by the ground is actually helping the person to move forward. So the friction here are in the direction of the motion of the person. Okay, so A is correct. The magnitude of sliding friction is always proportional to the normal force. That is correct as well. As we have seen, if k is just like a certain constant mu k times the n, with the n is the normal component of force. Rolling friction is much smaller than sliding friction. That's why we use actually tires, not sliding the the objects on the surfaces. So the friction here are smaller than that. That's why we use the rounded or circular shapes of tires to just like move faster. Friction are less. That's all for this video. See you in the next one.